Hello guys, welcome to NS Academy. So first things first, the scholarship test is still going on. So if you want to apply to the ISICMI course, check the description and join the WhatsApp group. The rest of the descriptions and information is already in the group. With that in mind, let us get back to the video. And in this one, we are going to learn about some special functions and some integral representations of functions like zeta function and polygamma functions. Now you might think, what is a polygamma function? We have learned about gamma function. Yes. So we will start with something that relates us to this gamma function and zeta function, and once we are done with that, हम आगे बढ़ जाएंगे into the polygamma function, and we will also see कि उसको हम कैसे evaluate करें. So this integral 0 to infinity x to the power s minus 1 by e to the power x minus 1 dx, right? This cannot be solved using any traditional ways you have learned in high school. So integration by parts will be useless here. Integration by substitution is not going to work here. You can try it if you like. But to do this kind of integrals, what we usually have to think is that, can I express this integral somehow as a form of an infinite series? It's a very common practice to transform integrals into infinite series and series back into integrals in order to evaluate them easily. It's a very common practice. So let's see what we can do here. First of all, I do not see a series representation for any of them, right? But understand this, that if I were to multiply e to the power minus x on the numerator and in the denominator, what will happen? I will simply get e to the power minus x. Now multiplying e to the power minus x with e to the power x will give me a 1. So this should be 1 minus e to the power minus x, and this should be x to the power s minus 1 dx. Okay. Now think about this. If I have this e to the power minus x wala expression here, does this remind you of something? The limits are from 0 to infinity, which means e to the power minus x is essentially less than 1, right? Because e to the power x will always be greater than 1, so e to the power minus x, which is 1 upon e to the power x, that will always be less than 1. So does it remind you of the formula a by 1 minus r in the infinite GP? It does, right? Can you write this like this? 0 to infinity summation n equals to 1 to infinity e to the power minus nx, and then x to the power s minus 1 dx. We can do this, right? Because this series here is exactly equal to this part here. And once you have done that, using Fibonacci's theorem, search it up. It's a theorem which allows you, wherever suitable, to exchange the infinite sum and the infinite integral, the improper integral, and you can switch the order of them. Switching the order of integration and summation is not always allowed. You have to be very careful about that. In this case, it is perfectly allowed, obviously for suitable values of s, as long as the integral converges here. Now, we understand everything is positive here, and also the integral converges, thus it is suitable to do these operations. And once we do that, you will see that we have n equals to 1 to infinity, 0 to infinity, x to the power s minus 1 into e to the power minus nx dx. I will leave this as an exercise for you to solve this integral, because this can be solved using the gamma functions which you have studied. You can see on the top right here, you can see the gamma function where I have explained everything. Now this will simply give you summation n equals to 1 to infinity. The x to the power s minus 1, that part will simply give you what? Gamma of s. And here you will have n to the power s. Okay. Now the summation index is n and not s. So gamma of s will remain as it is, and n equals to 1 to infinity 1 by n to the power s. This is the definition of zeta function of argument s. So simply the answer becomes gamma of s into zeta of s. Some special values include, if you simply put s as 2, so you can understand, if I put x as 2, it will simply get 0 to infinity x by e to the power x minus 1 dx would be equals to gamma of 2 and zeta of 2, right? Gamma of 2 is 1 factorial, zeta of 2 is pi square by 6. The answer is pi square by 6. So in this way, special values can also be found. This integral is a very useful integral in the field of physics as well. You will encounter these integrals if you ever decide to study higher physics. You will encounter this kind of integrals and a lot of other ways to evaluate integrals as well, because integrals and infinite series are of paramount importance in any science field, specifically maths and physics. So this should clear up how these integrals are so exciting. So we will move on to the polygamma and diagramma functions, and we will also see how these are and how the special values of them correlate with each other. So let's begin with the digamma function. Now, this is the function, this is the formula which we will require in knowing the properties and investigating them. Firstly, what is the polygamma or digamma function, right? Now, the polygamma function, as the name suggests, is composed of multiple gamma functions, right, in some order. So, polygamma function. Now, first of all, understand this. The case of only the first case of the polygamma function is called the digamma function. Now, what is the digamma function is what we are trying to understand. What is the digamma function? And then we can go back to polygamma because it would be easier to understand. Now, you know gamma of z is called the gamma function, right? We have learned about the gamma function. We know the integral representation of it. So, this is the gamma function. Now, the digamma function denoted like this or simply as psi of z can simply be said as ddz of ln of gamma z. So, log gamma, right? The derivative of log gamma is simply called the digamma function. And if you do the derivative, it simply gives you gamma prime of z by gamma of z, correct? Using chain rule, if you differentiate that. This is called the digamma function. If you differentiate the digamma function, you get the trigamma function. So you get the pattern. The trigamma would be like this, and it would be simply ddz or simply d squared dz squared of ln of gamma z. So twice differentiation of 2 times derivative of ln of gamma z. And obviously you can understand in this manner that psi of mz, this should be simply d m plus 1. So m plus 1th derivative of ln of gamma z, correct? And this is called the polygamma function. This is the polygamma function for any order m. So the first order where you have the 0th order, that is basically ddz, that is the digamma function. This is the trigamma function, and then as the order goes on, you can simply call it the mth derivative. And you can represent these things in terms of each other because they are basically derivatives of each other or integrals of each other, right? So if you go down the order, you have to derivative. If you go up the order, you have to integrate. Now, why are these useful and how can you find values of these functions? How are they used? So we are going to use something called the duplication formula in order to find out one specific thing about this, which is the value psi of half. Okay, we are going to find out this particular value. Now, first of all, this psi of half, in order to find that, we need to employ some infinite series as well in order to understand it better. So now let's begin with the finding the value of psi of half, right? Now, first of all, if we want to find the value of psi of half, the basic values psi of 1, psi of 2, these are defined, okay? So in general, if you were to simply find, let's say, so we want to find this first, okay? Now, in order to find this, we first understand that psi of x is nothing but n is from minus infinity to plus infinity 1 by n plus x, okay? This is the part. Now, with this part in mind, we can also see that psi of x is also ddx of ln of gamma x, right? Now, if we want to find this, we can use the duplication formula of the gamma functions. This can be verified using factorials that yes, indeed, this is going to be true. Now, if you take logarithm on both sides of this duplication formula, you get ln of gamma z plus ln of gamma of z plus half, and on right hand side you simply get 1 minus 2z into ln 2 plus half ln pi plus ln of gamma of 2z. That should be clear, right? Now, differentiate both sides. If I differentiate both sides, I know according to the definition of digamma function, differentiation of log gamma should be simply digamma, right? So log gamma ka differentiation would be psi of z. I'm not writing the 0 because in digamma you don't need to write the superscript. It's the first function in the polygamma series. For trigamma and above, you have to write 1, 2 as like that. But simply psi of z would denote digamma function. This would be digamma of z plus half. Okay. Now, what is this? According to chain rule, this should be simply minus 2 ln 2. This should be 0. And the last one, this should be 2 times and then the digamma function, right? So, 2 times psi of z. 2z, right? Shy of 2z. Now simply put z equals to half here in this equation. You will get that shy of half, which is what we want to find, plus shy of 1 equals to minus 2 ln 2 plus 2 shy of 1, because we put z equals to half. This cancels off and there is only one shy one, so therefore shy of half is nothing but shy of 1 minus 2 ln 2. Now shy of 1 is already known. It is known as minus gamma, right? What is gamma here? Gamma is called the Euler-Mascheroni constant. It's a very famous Euler's constant and it has values approximately 0.5772 and it goes on. It's a very famous constant and it appears in so many parts. So one example of this is of the harmonic numbers. Limit n tends to infinity, hn minus ln of n, or you can simply say log n, where c is nothing but Euler-Mascheroni. So this has relationships here. It relates with the harmonic numbers and the logarithmics. So yeah, this is going to be the derivation, and I don't think we need to delve much deeper into this, because if I go on, the video would be too long. There are so many integrations and infinite series that I can talk about, but let's end the video here. I hope you learned something new and exciting, and this might inspire you to do this kind of integrals or infinite sums in the future as well. And of course, if you're just a student preparing for JEE or ISI CMI type of exams, this knowledge is not exclusively going to help you in the exam, but knowing that you can do this kind of stuff to yourself is going to be a much more inspiring factor for you and a much more motivating factor to go for these exams, because you would know that what I know is already much higher than what the syllabus is in the exams. So this only makes you more confident towards it. Anyway, on that note, let us end the video. So those who are new to the channel, do subscribe. If you have any queries, let me know in the comment section.